assistant at the Concord Consortium. I work on a lot of the earth science projects that we have here under the direction of PI Amy Pallant and with our partners at Penn State, National Geographic, and Turk. So I work on several earth science projects. Geohazard is one of them, and the wildfire model, which I'm going to show you today, is part of the second installment of that. So the Geohazard Project is focused on allowing students to explore natural hazards and extreme events, the predictability and physical impact of those events, and the risk to human lives. So we allow students to investigate and observe the environmental factors that cause and propagate a hazard, and also reason about the impacts and risks that these hazards bring to communities. We created 3 natural hazard modules: hurricanes, wildfires, and floods. I'm going to show you the wildfire model today. You know, like most geoscience topics that you come across, teaching about natural hazards poses a lot of different challenges. It's on a huge spatial scale. The temporal scales can be also larger than many people are used to. And natural hazards are the result of interactions of many factors in a complex system, and wildfires are no different. So scientists rely on computational modeling as a way to explore such systems. And we also want students to explore those systems in the same way. So these computational models, like the Wildfire Explorer that I'm going to show you, provide opportunities for students to gain understanding of the underlying geological forces and forecasts of the locations and likelihoods of future events. And this also lines up well with what the next generation science standards call for in terms of natural hazards and their practices of using models, carrying out investigations, construction explanations, and so on. So the motivation for this project came from the increasing number of natural hazards that we've seen in about the past decade or so. And it doesn't, you know, there's been a trend of increasing hazards, and it does not appear that this trend is going to drop anytime soon. Unfortunately, as we can see here from the National Climate Assessment in 2018, just a couple years ago, they say that the cumulative forest area burned by wildfires has greatly increased between 1984 and 2015. With continued greenhouse gas emissions, fire frequency could increase 25%, and the frequency of very large fires could triple. So it's important for students to know, why these things are happening, what the impacts are, and if there's anything we can do to mitigate the risk, because we believe that a more informed public can be a better prepared public for the coming events. Nothing is different this year about wildfires, maybe that it's actually more worse than in past years. This is a graphic taken from the Fire, Weather, and Avalanche Center just this morning on the active burning wildfires in the United States this morning. All the red signifiers are fires larger than 1,000 acres, and the orange ones are smaller than 1,000 acres. And this brings up a lot of questions. Why have there been so many wildfires in recent years? Why are some fires bigger than others? Why do the biggest wildfires and the most frequent wildfires seem to occur in the Western United States? And what effect, if any, does climate change have on wildfire occurrence and intensity? And so these are all questions that we pose to students in the module, and we hope that the model and the curriculum module that comes with it allow them to investigate, observe, and answer these questions. One of the best ways we've found to get students to understand and have a framework for it is using the fire triangle, which is a widely known and used in fire agencies and prevention messages throughout the United States. We found that the fire triangle, with the ingredients of oxygen, heat, and fuel, provide a framework for investigation and reasoning that students do throughout the module. And then once they understand all the factors that go into the fire triangle, which I'll show you in a second, is that they can then start to predict and use their uncertainty and what they know about uncertainty to focus on the likelihood of the spread of wildfires and forecast coming events. So the factors that we can control with the Wildfire Explorer are shown here with their corresponding side of the fire triangle. Oxygen, in terms of wildfires, mostly means the air that we breathe. It's a majority of oxygen, right? So we allow students and users to control wind speed and wind direction in the model. Then if we look at the fuel part of the triangle here, we have two things related to fuel that you can control. One is the vegetation type, and the other is the drought level or moisture content. And on the heat side, you can place a spark simulating like a lightning strike or a discarded cigarette in the wrong place or an untended campfire, something like that. And also I put terrain on this side of heat, which seems a little weird, but we're actually gonna go through an example of that today to see why I put it here. Finally, here's some important links. If you want to learn more about this project, you can go to the Geohazard Project page. You can go to the specific wildfire page, or you can just go straight to the model, which I'm about to show you at wildfire.concord.org. So here is the Wildfire Explorer model. It is a landscape of 2 or 3 zones, each that can be programmable through the terrain setup window here. So if I go to terrain setup, you can see the factors that we can control for each zone. So in zone 1, you can see that it's mountains. The vegetation type is forest with large litter, which is large trees with lots of large logs and other things on the ground. For zone 2, we can see that it's a foothill. The vegetation type is a shrub, and it's in a mild drought. Finally, zone 3 is plains, and it has grass and medium drought. I'm going to actually make this burn faster by decreasing the moisture content. Now, if we go to the next screen, we can see a summary of what we just set on the previous screen, and we can also set the wind direction and speed here. So the wind direction and speed, unlike the other factors, it governs the whole model. So the wind direction and speed will be set for all 3 zones right here. I'm going to set it that way at 10 miles an hour, how about 8 miles an hour, and create. So you can see that the zones are colored by the drought level that we've set. So this was at no drought, but I changed it to mild drought, and you can see the color change. This one is at drought level, so it's a little yellower than these 2. I'm going to place a spark. I can place 3 sparks because it's a 3-zone model, and I could place them anywhere, but I'm going to start in each zone. And then we can click run. So what we see here is the red fire front burning the vegetation in its path and leaving behind a blackened area that has burned. Some places burn out or stop burning because of the computational equation behind it. So what's interesting and what's really cool about this model is that it's completely based off of real equations developed by the USGS. There's this guy named Dr. Richard Rothermel. Yes, his last name is Rothermel. I think that's kind of funny that he worked on wildfires. And he produced this about in the early 70s, and it's been touched up a little bit through the years, but this is the main equation that current wildfire scientists use to model wildfire spread. So whenever we go to the terrain setup window and we adjust the terrain or the vegetation type, which incorporates like the size of the fuel, the intensity the fuel burns with, and the closeness, how close the fuel is together, and the drought index, which is moisture content, and wind direction, wind speed, all those are inputs to the actual fire equation that Dr. Rothermel came up with. So you are literally adjusting the variables of the equation as you adjust the terrain setup window, and then those variables and the rate of fire spread is reflected in the model. So let's run a quick experiment here. We have 3 levels of terrain, so we can isolate that variable. So I'm going to make all other variables the same so we can investigate how fire spreads through terrain. Oh, go to zone 2, I'm going to make it shrubs and mild drought, medium drought. Zone 3 is on medium drought, and I'm going to change it to shrubs. So we'll be able to isolate the effect that terrain has on wildfire spread. So just real quickly in your head, try to think over which terrain the fire is going to spread the fastest, and then watch how it goes. So I just click start. And interestingly enough, qualitatively, we can see that fire spreads much faster in mountains than either hills or plains, which is not exactly an intuitive concept. Now, if we want more than qualitative, we also have a graph where you can see a quantitative representation of what's going on here. in terms of the acres burned over time. So here we have acres burned on the y-axis and time on the x-axis, and you can see that each zone has a line representing the number of acres burned. So zone 1 has clearly shot up way higher and the other two are pretty similar to each other. So why does fire burn fastest in the mountains? It's because the heat, if you start on the top of the mountain versus the bottom, we'll be able to see this as well. And we can see which one burns faster. So you can see that the fire at the bottom of the mountain actually burns much faster than at the top because the fuels higher on the slope get preheated by the fire below it, and therefore they lose a little bit of moisture and they more readily burn as the fire moves up the hill than down where they can't get preheated. So that is why, going back to the presentation, I put terrain on the heat part of it, even though it's not really a heat source of starting a fire. The terrain is related to the heat content that the fire produces and progresses its spread. Finally, there's a couple more features we have on this model. If we start it, we have some mitigation factors like a fire line, which we frequently see used to contain fires. So I can place one end of the fire line here and drag it to another. Now it takes some time for this fire line to implement because it's representing how it really is implemented, where people have to go out and dig these lines and clear the vegetation in a line to stop the fire. And we can see that we were successful. The fire stopped at our fire line. So that's really fun. I'm gonna decrease, I think it's all on medium drought already. Yeah, okay, I was gonna make it burn faster, but I can't. So what I'm gonna do is add some wind and we can get this fire really burning. My sparks are still there. I'm going to press start. We also have a helitek that you can implement and drop water on the fire. But with it spreading so quickly, a helitek really doesn't do that much. We can try the fire line. And this is kind of making it a little bit of a fun game. But the principle of this is that we have these mitigation tactics that are focused on decreasing the risk to a certain area. So I was trying to protect Evansville here. It didn't work because I didn't give it enough time to build the fire line. But these are kind of the inquiry things and investigation and trial and error things that we allow students to do with the wildfire model so that they can explore the effects of the different variables and also how these variables and mitigation techniques can reduce the risk to areas where fires are burning. So I think that's the end of my spiel. Do we have any questions?
I put in the chat for those of you who wanted to, the links. Others did too, so if you want to try playing with this. But if you have any questions at this point, oh, wait, we have Kim. Kim's hand is up. Go ahead, Kim.
Hi, Chris and Carla. I'm not understanding why the fire stopped spreading.
Right. So the fire, we first had it so that the fire just burned all the time everywhere. If it started, you could not stop it. And we saw, after talking with fire scientists and witnessing real fires in the West, you don't have to contain the whole thing because they don't just continually burn if they start. Right. So it's a ratio between the burn index of the fire, which takes into account the fire intensity and all the factors that I've mentioned here that go into the thermal equation. And if those are below a certain level, then if the fire intensity is below a certain level, the fire will kind of stop and put itself out rather than just continually burn.
But I don't know very much about fires at all, and I don't have any physical sense at all about why that burn ratio would peter out over time.
Yeah, it was a while ago when I, first was researching these equations, so I'm trying to remember it. But based on this, the fire intensity is not constant throughout the burn time. right? If it goes down a slope, the fire will decrease in intensity. If it hits a patch of moisture, it will decrease in intensity. So based on those factors, the burn index takes into account how, if the fire is burning through grass, which burns very intensely but not very, or burns very quickly but not very intensely, versus forest with large litter where large fuel is set on fire and it burns extremely intensely and can get to the crown of the forest and start burning even more intensely there. And it just takes into account those kinds of things to stop itself.
So I noticed it stopped when it got to the river, and I thought that was extremely cool. I understood that. I noticed that it stopped when it got to the ridge crest. I thought that was extremely cool also. I like that a lot, but I still don't have a good mental or sort of a mechanistic sense of why it just stops after a while when it's just going across the plain old darn near plains. But we don't need to take up the whole Q&A time on my
I'll email you
fire
about
curiosity, but if you were to email me, if you can figure that out, I'd love to hear.
Cool.
So Becky says natural fires do burn out. I do know that, and I do recognize that this model is replicating the behavior of actual fires, but I don't understand why actual fires burn out. I like that the model does what the actual fires do, but I don't understand what it is that the actual fires are doing. But Crystal will explain it to me in an email, so thank you.
Anyone else? Feel free to ask a question. You can unmute yourself and just speak. Questions, thoughts, maybe on using this with kids, with your students?
I see someone put in, why don't we have extreme drought? That's a great question. And in the module, we are able to preset more things than I've shown you here. So right now we don't have any, you can't adjust the terrain at all. And we have in some models in the curriculum, you can adjust the terrain. And we also, towards the end of the module, when we kind of prompt students to think about risk in the future, we introduce an extreme drought scenario where things are much more drier than they are now and fire burns much faster. We have them think about the risk and impact that causes to mitigation techniques and people. That's a good question.
I see a question about, can fire lines be added after the run or only before?
Fire lines, so it just restarted. Fire lines can be implemented during a run. You can't put them in before, but if I start it, the model stops when I click fire line, and I can, I'll try to predict Evansville here. You can click and drag and place a fire line. Again, there is a delay before the fire line actually goes into effect. You can see that we have, well, for now, effectively protected Evansville. So you can only place it before or during a run.
So Trudy's message said in the chat that it's being embedded in a curriculum module, which I know is not ready to be released yet. But can you just give us a quick glimpse about what kind of things are in the curriculum, what kinds of guidance or activities are set up for kids to do?
Yeah, absolutely. The curriculum module is in beta testing. We have put it in front of students and teachers, and we're getting some data back, and we're going to revise it and send it out to the public in a little bit. So what we do, we walk them through the variables one at a time, kind of what is the effective wind speed, what is the effective wind direction, wind speed go together. Drought level, has your town experienced a lot of rain recently, or does it have a little bit of rain? How do you think that affects the spread of wildfires if a wildfire were to come here? And we give a lot of real world case studies as well. So once they understand the effects of drought, moisture content, terrain, and all the factors, we'll give them an example of like the campfire in 2017 in California and say, these were the conditions when the campfire started. Do you think that there's a high risk that it will spread, or do you think it will kind of put itself out because the moisture is really high and it's in a flat area, things like that. So really try to always bring it back, one, to the fire triangle, and two, to case studies. I can give you more information if you would like.
How much time are you envisioning that classes would spend on this curriculum?
We have a 5-activity module with each module with, sorry, a 5-activity module with each activity supposedly taking about 45 minutes of class time. So it's designed to go in one 45-minute class for a week.
Mm-hmm. Yep.
We find a lot of teachers like to, do supplemental things that more maybe relates it to the area they're in and things like that. So it can take longer.
Mm-hmm.
Does anyone else have, oh, how will we find out when the curriculum is available? I'm thinking, Chris, that we can email these folks.
Yeah, we'll email everyone that has attended this and let you have first dibs at it.
Right. Anyone else have any questions?
Hi there. I just had a super quick question. Thank you for the presentation today, Chris, appreciate it. What were some of the early ideas that you introduced, the fire triangle and some of the activities that are introduced at different grade levels with that?
So we don't have a specific module for different grade levels. We have one module that is for, grades from 6 through 10 really, or, you can use it anywhere. What was the second part of your question, sorry?
I guess just how were an idea such as oxygen for middle school versus high school, or how these ideas branch to the model. I guess they use that fire triangle like you mentioned, and then what are some of the, if you have an example, or if you don't, just some of the early ideas that progress to this simulation that we're looking at today. I think you sort of mentioned it earlier, that you brought up the fact that these ideas are brought in for the campfire that they can build into this model. But are there do you have any other examples maybe of the use of the fire triangle or some of the activities that went along with that?
Sure. So we do believe in, starting, with their discovering first rather than telling them a lot. So we introduce the fire triangle and say, many of the components that you're going to see here are incorporated into the fire triangle and can be explained by the fire triangle, explaining why a fire starts out or why it progresses or why it doesn't progress. So we introduce the fire triangle and kind of just let them loose on the model and say, what happens if you set wind speed to higher and higher wind speeds? How does the fire spread react to that? Or what happens if you put a spark at the top of a mountain versus the bottom of a mountain? What happens to fire spread, and in which case does fire spread faster? And then we bring them back and say, okay, well, you've seen wind speed, you've seen terrain. Where do you think these things fit into the fire triangle? On which side do they correlate to? So we have a common set of questions. We use the CER, claim, evidence, reasoning sequence. We've also added a risk element onto that, risk or fire triangle element onto that. So we'll ask them to make a claim, which wind speed caused fire to spread the fastest? And then evidence is, use evidence from the model, either qualitative or quantitative from the graph, that helps explain your claim. And then go to the reasoning. Well, why does, a higher wind speed cause fire to spread faster? Because it pushes the fire faster across the landscape, spreads the embers faster, right? And then we say, well, okay, so in what situation would there be a higher risk if there was a low wind speed or a high wind speed? Hopefully, and you say, well, risk is the likelihood of impact, so a higher fire spread would be a higher risk. So that's a common sequence that we have for them investigating the factors relating it to the fire triangle, using the model to answer questions, and then reasoning about what they've found.
Thank you, Chris.
You opened your talk with the climate change connection, that wildfires were becoming more frequent over time. Do you
Mhm.
build up to that point in the curriculum? How do you get to that point?
Right. So we have them, experiment with these factors, and then the main way we get them to target that is we introduce extreme drought, and we say, California has seen more and more drought and more severe droughts in the past couple of decades. Scientists project that these trends are going to continue, and how do you think that affects fire spread, fire intensity, mitigation techniques like that. So that's almost the whole fifth activity is looking toward the future and how in the future the conditions for promoting wildfires is probably going to get worse.
I'll point out that Trudy put in the chat that there is a teacher guide also that accompanies the module, so that also provides suggestions. And I'll mention that the pedagogy behind this is both claim evidence reasoning and ambitious science teaching. And those are both sort of interwoven into the model, into the module for teachers and students. All right. Anyone else?
Thank you, Trudy, for answering the questions in the chat.
So I just wanted to say that I think it's very cool that Unit 5 looks towards the future, because historically earth science education has mainly focused on the past, and earth scientists are thought to think about the past with lots and lots of different, we spend entire courses in college and graduate school learning to think about the past in all different sorts of clever ways. And it's somewhat of a new shift for earth scientists to, society is now asking earth scientists to think about the future. And that is not something that our profession has been doing all along. And the big distinction is that if you just want to think about the past, you can do that with just data. But if you want to think about the future, you need a model. So data lets you think about the past, but if the whole profession has been reoriented to now we ought to be thinking about the future, society needs us to think about the future, that's very tightly coupled with the rise of use of modeling in the profession. Because if you want to think about the future, you need a model. So, I'm intrigued by the idea that you've got one of the 5 units totally devoted to thinking about the future.
Great.
And that is actually the same, Kim, for the hurricane module. In the end, that's the same guiding question.
How will hurricane risks and impacts change over the next 100 years? Mm-hmm.
Yeah, exactly.
And the flood module, which is coming soon.
That's true. Well, if anyone has any other burning questions, I don't want to cut you off. You seem to be going more half hour than 15 minutes, but that's okay. Otherwise, I'd like to say thank you very much for attending. And Chris, if you can put up that last slide briefly,
Yep.
I'll just indicate what's coming up. So next Wednesday, Don Haas from the Paleontological Research Institute is going to be sharing a new interactive site they have created, Earth at Home, which has digital encyclopedias, virtual field trips, a whole bunch of different resources. The registration again for that is the same. The bit.ly is there, and I'll be emailing folks. But if you have not seen this resource, it's really quite amazing. It's a new sort of packaging from the Paleontological Research Institute. So that will happen next Wednesday at noon Central Time. And thank you so much, Chris, for your presentation and willingness to answer questions. This was fantastic. And thanks to all of you who came.
Thank you very much, Carla.
righty.
Thanks, Chris. That was fun.